Given that e to the power x equals 1 plus x squared on 2 factorial plus x cubed on 3 factorial, and so on off to infinity, find in terms of pi an approximation for e to the power of I pi in the form of x plus iy, using the above 4 terms of the series. Part B, use your calculator where necessary to plot this approximation on an Argand diagram. Part C, if z is any complex number, prove that z to the power n plus z conjugate to the power n and e to the power z plus e to the power z conjugate are purely real numbers. So the first part, A, we're looking for e to the I pi. Now that just means we're subbing I pi into this expression. So that's e to the I pi equal 1 plus I pi plus I pi all squared divided by 2 factorial plus I pi all cubed divided by 3 factorial. Alright, so 1 plus I pi. Now I'm going to get I squared, pi squared, and I squared is -1, so I have minus pi squared over 2 factorial. I should put dots off to infinity. Plus, now, in fact, it's going to be a minus because I'll have I cubed, and I cubed is equal to I times I squared, which is -I. So I'll have minus I times pi cubed on 3 factorial, and so on off to infinity. And then just collecting the like terms, I can say that e to the power I pi is approximately equal to, and using just the first 4 terms, it's approximately equal to 1 minus pi squared over 2 factorial plus I times pi minus pi cubed on 3 factorial. And this is our approximation for e to the power I pi in the terms, in the form rather, of x plus iy. For part B, we have to use our calculator to plot this on the Argand diagram. So, using our calculator, we would get that e to the I pi is approximately equal to, now let's have a look, 1 minus, I don't know if you can see very well, 1 minus pi squared over 2 factorial, which is 2. So that's -3.9348. Let's just put a few decimal places. And then for the imaginary part, that's going to be pi minus pi cubed over 3 factorial, which is 6. And that's negative, of course, timesing by I, 2.0261. Alright, and so I need to plot this on the Argand diagram, so a very rough sketch. We're going to be somewhere in the 3rd quadrant. So let's say this is 1, 2, 3. Let's extend that a little and make this 4. So this is -4 here. I will be somewhere at about, say this is 1, that's 2. So I would be roughly sitting here, e to the I pi. This is an approximation of e to the I pi, and that's where my approximation will lie. Let's indicate that as -2. Okay? And the final part, proving that z to the power n plus z conjugate, or z bar to the power n, is real, and also proving e to the z plus e to the z bar is a real number. So, for the first part, z to the n plus z to the, or z bar to the power n. Okay, now let's say that we let z equal to cos theta plus I sine theta, and of course we need to times by r. So it's r cos theta plus I sine theta, and we can abbreviate that if we really want to r cis theta, just to make it shorter when we're writing, because we're lazy. As mathematicians, we usually are lazy. So anyway, continuing on. we have z to the n plus z to the, or z bar to the n equal to r cis theta to the power n plus r cis of negative theta, because I've taken the conjugate, so that means I could put a minus in here, and if you don't know why, I'll show you in 1 second. So using de Moivre's theorem, r to the n cis n theta plus, what do we have, r to the n cis minus n theta. I can factor out r to the n, and now I can rewrite it as cos n theta plus I sine n theta. Now it's plus cos of negative n theta, but cos is an even function, so cos of negative n theta is the same as cos of n theta. And then plus I sine of negative n theta. But sine is an odd function, so sine of negative n theta is the same as minus sine of n theta. So I have minus I sine n theta. And then you'll see that this negative I sine and this positive I sine will cancel, and I'm left with r to the n. Adding these will be 2 cos n theta. And this is purely real, which is purely real. Now for the next part, let's just grab some paper. What do I have? I have e to the z plus e to the z bar. Well, going back into my, what's this called, formula given for e to the x, I get 1 plus z plus z squared on 2 factorial, and so on, z cubed on 3 factorial. That's for e to the z. And now for e to the z bar, it's 1 plus z bar plus z bar squared on 2 factorial plus z bar cubed on 3 factorial, and so on. Now let me move this away and continue working with what I have here. Now I will take the ones and put them together, so 1 plus 1, okay, that's obviously 2. And then I'll have z plus z bar plus z squared plus z bar squared over 2 factorial. And I'll put these in their own little bracket. And I'll have z cubed plus z bar cubed over 3 factorial. And I'll put that in its own little bracket. And so on off to infinity. And now we'll use what we just proved in the previous part for C. Where is it? Here. That this term is purely real. Where is it? Can you see? No, you can't. This term is purely real. So let me write this now as, alright, a sum from n equal to 0 to infinity of z to the power n plus z bar to the power n, all divided by n factorial. Now, is this the same as this? Well, sure it is. If n is 0, this is z to the 0, which is 1, plus z bar to the 0, which is 1. So that's 2 in the numerator, divided by 0 factorial, which is 1, and we get 2. For the n equals 1 term, we recover this term here. For the n equals 2 term, we get this term. For the n equals 3 term, we get this term, and so on. And what did I work out in the previous part? I worked out that this expression was equal to 2r cos n theta. So this is 2, that's 2r to the n actually, 2r to the n cos of n theta divided by n factorial. But this here is the sum of an infinite number of purely real numbers. So this itself is purely real. So I can say this is purely real since it's the sum, it is the sum of an infinite number of purely real numbers. an infinite number of purely real numbers. And there we have it. We've proven that e to the z plus e to the z bar is a purely real number for all values of z.